Hello viewers and welcome to today's session. So today we'll be focusing on physics paper 3, that is code 232/3. And in today's video we'll focus on preparation for KCSE in physics paper 3, and we'll be having 5 areas which we'll be focusing on. The first area is topics and concepts tested in physics paper 3. We have the instruments used and their accuracies, how to fill the tables, solving of the equations, and lastly we'll be looking at how to plot the graphs. So we start with the accuracies. So it's important to note that any reading that you take from a measuring instrument must be recorded in accordance to the accuracy of that instrument. So that means if you are taking any reading on a physics practical from a particular instrument, then you must record it in accordance to the accuracy of that instrument. And by accuracy, we mean the smallest division on the scale of that instrument. That is the value. So for example, in a meter rule, the smallest division is 0.1 centimeters, and that means any reading you take from a meter rule must be recorded in 1 decimal place in centimeters. Then we have vernier calipers. So the readings should be recorded in 2 decimal places in centimeters. That means that, for example, you have 0.01 centimeter, which is the accuracy of a vernier caliper. We have micrometer screw gauge. So the accuracy is 0.01, but now in millimeters. So that means any reading you take from a micrometer screw gauge must be recorded in 2 decimal places, but in millimeters. Then we have a stopwatch. The scale, the accuracy is 2 decimal places in seconds. We have the ammeter. So for the ammeter, most of the ammeters have more than one scale. So the value recorded should be a minimum of 1 decimal place. That means any reading you take should be at least 1 decimal place, depending on the scale you have used. Then we have the voltmeter. So that is the same case to the ammeter. It should have at least 1 decimal place in one decimal place in volts, depending on the scale you have used. Then we have a thermometer. The thermometer scale should be in whole numbers. So that means, for example, you can get 10 degrees, 15 degrees as whole numbers, because the accuracy is 1. That is 1 degree Celsius, a whole number. So those are some of the instruments we commonly use in physics. And it's important to note that when you are referring to accuracy, suppose, for example, you have taken a reading with a meter rule and you found the answer is 12.5 centimeter, but now you realize that they have already indicated the unit, whereby, for example, they have given you dash meters. So in such a case, you must also carry the 3 decimals when it comes to meters, such that, for example, if you have 12 centimeters, 12.0 in centimeters, in meters it will be 0.120 meters. And that means that that decimal is also very, very important for the sake of accuracy. So that is the first part on accuracies. So I want us now to go to the second part, that is the topics tested in physics paper 3 and the concepts that are tested in physics paper 3. So we'll start with the first topic. We have 7 areas which we'll be focusing on, but now let's start with the first one, measurement 1 and 2. So in measurement 1 and 2, we have using a meter rule, a vernier caliper, or a micrometer screw gauge. So for meter rule, we normally use them when you are measuring distances. For example, when you are balancing things on a meter rule, or maybe you can use it directly. Maybe when you are measuring distances, maybe when doing experiments on thin lenses, curved mirrors, among other things. Then vernier calipers are normally used when you are measuring the diameters. For example, the diameter of a boiling tube. Then we have micrometer screw gauge. mostly when we are measuring the thickness or diameter, for example, of a nichrome wire. That means all candidates should be able to know how to use those measuring instruments. Let's go to the second topic, cells and simple circuits, and also current, electricity too. Cells and simple circuits is in Form 1, while current, electricity 2 is in Form 3. So in this case, we'll be looking at 4 practicals on electricity. These are the major practicals. So, and in this case, it's important to note that the concepts tested in these 2 topics are 4. 1, to measure the resistance of a metal. Number 2, to measure the EMF of cells. Number 3, the internal resistance. And lastly, the resistivity. So we have the resistance, we have the EMF, the internal resistance, and lastly we have the resistivity. It's important to note that the resistance is for a metal wire or a nichrome wire or any other thing, but the internal resistance is for the cells. So let's start with the first experiment for Ohm's law. So we have the cells, we have the switch, variable resistor or a rheostat. We have another coil, a coil of a resistance wire. We have voltmeter and ammeter. Then you're plotting a graph of voltage against current. So when you're plotting a graph of voltage against current, you realize that the graph is a straight line passing through the origin. And this indicates that voltage is directly proportional to current. So from the correlation in Ohm's law, the slope of this graph, which is a change in voltage divided by change in current, represents the resistance. Remember, R is V over I. So that means the slope of this graph represents the resistance. And that is for Ohm's law. We go to the second experiment, number B. So we have the cells, switch, ammeter, voltmeter. We have variable resistor. Then you are filling a table of current. You are already given the values of current, so you are determining voltage. Then from there you fill the resistance column or row, and then you fill the reciprocal of current row. Then from there you plot a graph of reciprocal of current against the resistance. The reciprocal of current against the resistance. So again, this is a straight line graph. And you realize that this straight line graph, all straight lines obey the equation of y is equals mx plus c. So that means from the general equation, EMF is equals V plus IR, whereby we are saying EMF is equals to terminal voltage plus the internal voltage or the lost voltage. So we all know that the terminal voltage or the terminal voltage or PD is given by IR. So that means EMF will be IR plus the lost voltage, which is IR small r. So, and when you rearrange in the form of y is equals mx plus c, you multiply through the equation by 1 over IE. And then you get 1 over I equals R over E plus R over E. So you realize that 1 over I is the y-axis. Then we have R, which is the x-axis. And that means the slope of this graph represents 1 over E, which will be our M in this case. So the slope represents 1 over E. And then so that means if you want E, the EMF, you simply find the reciprocal of the slope. Then we also have R over E, that is small r. So R over E also is represented by the intercept, the reciprocal of current intercept. So the reciprocal of current intercept will give you the R over E, whereby you already got E from the reciprocal of the slope. So that means you can get R by multiplying E by the intercept. The value of the intercept you already have, you multiply by E, and then you're able to get R. So we go to the third practical. That is a practical on we have voltmeter, ammeter, nichrome wire, the switch and the cells. Then you're also feeling a table of voltage against the voltage and current. Then you plot a graph of voltage against current. So you realize that this is a this is a straight line graph as well, but this time round with a negative gradient, meaning voltage is inversely proportional to current in this case. So, and from this graph here, you'll be able to understand that it obeys also the equation of EMF. So we have EMF is equals terminal voltage plus lost voltage. And when you rearrange in the form of Y is equals mx plus C, that means you make V the subject of the formula. So it will be V equals negative IR plus E, whereby you took negative IR on the other side. So in this case, V is the y-axis. We have I, which is the x-axis, and that means slope M is negative R. The slope is negative R. Then we have E, which is the v-intercept. So that means because slope represents negative R, this negative in the R will be cancelled by the negative of the slope, because for any graph whereby the left hand is above the right hand, then it simply means that this is a graph with a negative slope. And that means the negative of the slope will be cancelled by the negative of the R. That means R will be positive. And also the EMF, you read it directly on V-intercept. So those are the first three practicals. We can also look at the fourth one before we go to another summary of the same. So for this practical, we have cells, we have ammeter, we have a switch, nichrome wire, and then this time round you are given the values of length on the nichrome wire. Then you are reading current and the reciprocal of you determine the reciprocal of current. So that means we do not have a voltmeter this time round for this particular case. So then you plot a graph of reciprocal of current against length. So you realize that again this is a straight line graph. This is a straight line graph whereby as you increase the length, then the reciprocal of current will be increasing. That means length and reciprocal of current are directly proportional. It's important to note that the reciprocal of current is the same as resistance, because the opposite of the current flowing. So that means the two are directly proportional. The more you increase the length, the more the resistance increases. In other words, the current will be lesser and lesser. So in this case, you are given the equation, the general equation, 1 over I is equals KL over AE plus Q over E, whereby you already got A, cross-section of the area of the nichrome wire above with there. So for that case, you normally use the micrometer screw gauge. First of all, you determine the diameter of the nichrome wire, and then from there you get the cross-section area by applying pi r squared, but in SI units. So and then from there you got the EMF from above there again. That means you are given some small circuit which you would use to determine the EMF of the two cells. So from there, that means what you don't know in this equation is K and Q. So you are using this equation to determine the values of two constants, K and Q. So what you do for this particular equation, again, it is in the form of y is equals mx plus c. So that means you have to interpret this equation. So 1 over I is the y-axis. We have L is the x-axis. That means slope represent K over AE. K over AE, whereby you already have A and E. So that means you already need K only. So in this case, once you get the slope of this graph, then you can see the answer of the slope is equals K over AE. Then you replace the values of area and EMF as you got from above there, the values you got. And then the slope, that means what you do not have is only the K. Then you can be able to get it. Then Q over E represents the intercept. The I over E intercept, that is Q over E. That means the value you read from 1 over I intercept, the value you read from I over I intercept will definitely give you Q over E, whereby you already knew the value of EMF. So, and then the other one you have read from here, so you can be able to get Q. So those are the four major graphs on photoelectric, the four major graphs on current, electricity too, and also cells and simple circuits. So it's also important to note that these experiments on current, electricity, and cells and simple circuits can also be used to determine the resistivity of the wire, whereby if you are looking for the resistivity, then it will be given by area times resistance divided by length, AR over R, which can also be given by, because we know R is V over I, from Ohm's law, it can also be AV over high L. And it's important to note that if you have drawn a graph of voltage against current, then V over I will be the slope. V over I will be the slope. Then it still remains the area, and L remains the length. So in this case, you can be able to get the resistivity by replacing the values, and the resistivity, the value will be given by in ohm meter. That is the value will be given in ohm meter. So that is all about the second topic on cells and simple circuits, and also current, electricity. So we go to the third topic, that is the turning effect of force in form 2, equilibrium and the center of gravity, also in form 2, and then we also have floating and sinking in form 4. So these four topics normally are tested together. So, and in this case, you are determining first the position of COG, that is for the meter rule. You are determining the position, the balance point, the position of COG. Then from there, you also determine the width of the second solid, whereby you are given the first solid to put a particular distance from the pivot or the COG, and then you determine the width of the other one by saying F1 D1 is equals F2 D2. So from there, you can also use this experiment to determine the upthrust in the liquid, and also the relative density, whereby you are given two liquids. So you determine the upthrust in the first liquid, then the upthrust in the second liquid. Then you can be able to determine relative density by saying upthrust in liquid 1 divided by upthrust in water. So we have the experiment. As you can see, the COG is normally 50.0. Remember we said any reading on a meter rule must be 1 decimal place in centimeter. So this one could be the balance point 50.0, can also be 50.1, can also be 49.9. So once you get the COG, then you can hang the first mass in some given distance. Then you are given the second solid, which you are supposed to get the balance point. So once you get the balance point, that is distance D, the Roman 1, then distance, then force 2, the weight of the second solid can be obtained by saying F1 D1 is equals F2 D2. That is the principle of moments. Because this system is in equilibrium, so the sum of clockwise moment is equals to the sum of anti-clockwise moment. So you can get the weight of the second body, and also after getting D, which is the balance point. So once we are done with that, we can also consider the second part. So we have the same solid, but now the other solid is submerged into the water. So again, you are looking for the balancing point. So you will adjust the position of the 100 gram mass until the system balances. Then you get distance D. Then from there, you are now required to get the upthrust. So because you have the weight of the solid at the first distance, then you have the second solid that you require the upthrust. So it's important to note that force 1 D1 is equals force 2 D2. And that will give you the downward force in the second side. So you have the downward force in the first side and the downward force in the second side. And then the upthrust for the second side will be given by the real weight of the solid submerged in the water minus its weight in the water. So you have its real weight in air minus its weight in the liquid. In other words, force 2, if you want half thrust, you simply say force the weight of the solid in air, solid 2, minus force 2, whereby force 2 is the downward force. In other words, it's right to say the weight in air of the 50 gram mass minus force 2, which is now the downward force in the water, will give you the upward force, which is the up thrust. That means downward force is weight, upward force is up thrust. So that means force 2 is weight in air minus up thrust. And that means if you have force 2 and you have real weight, then the up thrust can be obtained directly by saying weight in air minus force 2, which is the downward force in water. And then suppose you do the same experiment with another liquid, and then you get the up thrust for the second liquid, then it simply implies that relative density of the second liquid can be obtained by saying up thrust of the solid in liquid divided by up thrust of the solid in water. So those are the two ways you can use to, that's the way you can use to get the relative density. Up thrust of the solid in liquid minus up thrust on the solid in water. Remember, there is also another alternative whereby you can take the weight of the solid in water, the weight of the solid in the liquid divided by the weight of the solid in water. The weight of the solid in the liquid divided by the weight of the solid in water can also give you the up thrust. So we go to the fourth topic now. That is linear motion in Form 3. So for linear motion, you normally have oscillations. So for example, you have a pendulum bob. Then you are considering the length. So that means you'll be varying the length. For example, 20 centimeter, 30 centimeter, 40, 50, 60 centimeter, and so on and so on. Then you determine time for 10 complete oscillations, and once you get the time for the 10 complete oscillations, then you determine period. That is time for 10 oscillations divided by 10. You get the time for one oscillation. Then we have frequency, which is 1 over t, or 1 over period. Then we have t squared. Then you are plotting a graph of t squared against L. A graph of t squared against L. So you realize that the slope of the graph will be t squared over L, or change in t squared divided by change in L. So, but from the general equation, we all know that from the general equation that period is given by 2 pi square root of L over G, where G is the pole of gravity. So this is a general equation. Remember, in this case, you are determining the pull of gravity, the acceleration due to gravity. That is the important thing you are looking for in this topic. So, and that means your interest is G, the pull of gravity. So we all know the general equation is that T equals 2 pi square root of L over G. And then if you make T over L the subject, if you make T squared over L the subject, that is by doing some retro mathematics, for example, squaring both signs and then dividing by L both signs. You square both signs, then you divide by L both signs. Then you realize that T squared over L will be 4 pi squared over G. We all know the value of pi, so what you don't know here is the G. Remember, T squared over L is the slope of this graph. And that simply tells you that G, which is a pull of gravity, will be given by 4 pi squared over slope. So that means G will be given by 4 pi squared divided by slope, because you know T squared over L is slope. And that means if you cross multiply, then G will be 4 pi squared divided by slope. So we go to, that is the fourth topic on linear motion, where you are determining the acceleration due to the Earth's gravity. We go to the next topic, refraction of light. Reflection of light. So in this topic, we'll start by looking at this experiment here. So first of all, in the refraction, your interest is the refractive index. the refractive index of glass prism, water, or any other liquid. We have the refractive index of a glass prism, some or water, or even some other liquid. So in this case, for example, you can consider this experiment. We all know this experiment. That is the experiment on a glass prism. So whereby you draw the normal line, then you measure the first angle from the normal. So once you get the first angle, then you put two pins at some distance from each other, two pins, pin 1 and pin 2. Then after replacing the glass prism on the trace outline, then you look through the other side of the glass prism to get pin 3 and pin 4. So you have pin 1 and pin 2. Then you are using the other side to get a value of pin 3 and pin 4. So, and then once you get them in a straight line, you'll be able to get the angle of refraction by measuring the angle R indicated here. It's important to note that if you prolong the line of angle of incidence, the line forming the angle of incidence, it is parallel to the line that is on the angle of refraction. So the two lines are always parallel, and the distance between them is known as lateral displacement. That is distance d between the two parallel lines. So then the angles, you realize that, for example, the black line will form the first black line on the refraction. The second blue line will form the second blue line, which are also parallel. The third line will also form another third line. The fourth green line will also form another fourth green line. All of them are in pairs of parallel lines, whereby now if you get various values of angle of incidence, values of angle of refraction, since you'll be given the angles of incidences, then you can get sin I and sin R from calculators. If you plot a graph of sin I against sin R, so this graph is a straight line passing through the origin and with a positive gradient. So, and it's important to note that the graph here is change in sin I divided by change in sin R, which definitely is a refractive index. That means if you have this kind of a graph and then you want to the refractive index, then definitely you're only determining the slope. Then it's important to note that for this experiment, you may also draw the graphs using lateral displacement. That is sin I against lateral displacement. So it can also be drawn sin I against lateral displacement, and maybe other similar cases. So we go to the second part of refraction of light, still on determining the refractive index. So we have the glass prism, then you have the first two pins. We have the first two pins. We have the first pin, the first pin at the very far corner and the middle of the glass prism. Then you have two pins, whereby you are through the eye, you're focusing the pin 1, so that the other two pins are forming one straight line through the eye. So you are focusing pin 1 to make two more pins in a straight line. Then through the eye again, you are focusing on this other side, the pin 1, so that you see them in a straight line, and then you join them with the straight lines. So once you get the two lines, you join them and extrapolate, you realize you get a point S where the two lines are meeting. So in this experiment, you realize that you have the real depth of pin 1, that is from R all the way to P1. R all the way to P1, that's the real depth of the pin P1. But when you look through the two edges, through the two sides, you realize that you are seeing pin 1 at point S, because that's the point where they are forming a straight line. That means there's some form of displacement or reflection. So in this case, if you take the real depth divided by the apparent depth, that is RP1 divided by RS, that will give you the refractive index. So the refractive index will be given by the real depth divided by the apparent depth the real depth divided by the apparent depth, that is RP1 divided by RS. So that's the way you can get the refractive index. We can also consider the third setup here for reflection, whereby in this case we have some water in a prism, some water in a beaker, and then we have the pin down here, the object pin. Then you have a search pin attached to the cork on a glass rod, which is together with a meter rule. So whereby now you are focusing through the eye perpendicularly through the water to see the point where you are seeing pin 1. So you are looking for pin 1 through perpendicularly through the water, and then the point where you miss, you see the pin, you search with the search pin on the cork, so that the two pins, the object pin, the search pin together with the image of pin 1, the object pin, are coinciding without any parallax error. So, and that is now the point we have here. So from there you have now the real depth, that is D, divided by apparent depth H, whereby apparent depth is a point where now you are seeing the object pin after being refracted. So the refractive index can be given by real depth divided by the apparent depth. So real depth is a distance D, apparent depth is distance H. So that's a way you can use to get the refractive index, real depth of apparent depth. So it's important to note that you need to try this so that you can have more experience, and then you can be able also to understand more on what we mean by this, and you can gain the first-hand information. So we go now to the sixth topic, that is thin lenses, reflection at curved mirrors, and also linear propagation of light. Thin lenses is in form 4, reflection at plane mirrors and curved mirrors is in form 1 and form 2. Curved mirrors is in form 2, plane mirrors is in form 1, and also linear propagation of light in form 1. So in this case, your interest is to get the focal length. The focal length of the mirrors, that is your key interest. To get the focal length is the major interest or the concept you are looking for in this topic. So you have the first setup, we have the candle, and you can see how the rays are going through the lens all the way to the screen after refraction. So the candle is the object. Then we have the object distance u from candle to reflecting surface, which is the lens. Then we have the image. Remember, the image is being formed by the lens on the screen, so the image distance is from lens all the way to the screen. We consider the second setup whereby we have a concave mirror. Remember here above here we have convex lens. Convex lens, also known as the converging lens. Convex lens, the surfaces are curving out once, so it's still known as convex lens, but this is a converging lens. But now for mirrors, we are using concave mirror, which is still a converging mirror. So we have the candle as the object, the rays from the candle striking the mirror and then focused on the screen. The rays from the candle focus touching the mirror, then they are focused on the screen. It's important to note that sometimes they can converge in front of the candle. That means the screen sometimes may come all the way to the front of the candle, depending with the position of the object. Then we can look at the three major graphs. We have a graph of 1 over v against 1 over u. So that in this case, the graph is as you can see here. Remember, the left hand is above the right hand. That means the slope is negative here. But our interest in any graph is either the slope or the intercepts. In any graph you draw, the interest is the slope or the intercepts. But for this case, our interest is the intercepts. So if you look at the general lens formula, 1 over u equals 1 over f equals 1 over u plus 1 over v. That's the general lens equation or the mirror formula. 1 over f equals 1 over u plus 1 over v. But when 1 over u is 0, then it means when 1 over u is 0, it means 1 over v is equals to 1 over f. That's why we are saying 1 over v is representing 1 over f. Then when 1 over v is 0, then it means 1 over u is 1 over f. That's why we are saying the two intercepts are both representing 1 over f. And in this case now, it now means that if you want the value of f, you determine the average of the f you obtain from reciprocal of 1 over v here, then the other reciprocal of 1 over v here, 1 over u. So the reciprocals of the two intercepts will give you the focal lengths. That's the two focal lengths, and then you can be able to get the focal length by getting the average of the two focal lengths, because you are saying 1 over f is the intercept. 1 over f is the intercept. So if you get reciprocal of the intercept, then you get f, and then the two reciprocals will give you the two f's, and then the average will give you the correct value of f. Then you can also consider a graph of u plus v against uv. So this graph is still a straight line graph with a positive gradient and also passing through the origin. So in this case, you realize that from the mirror formula or the length formula, you realize that if you take the LCM and then the reciprocal, then you find that the slope, which is u plus v against uv, the slope will give you the value of the focal length. So that means if you are trying to find the focal length of this graph, you are simply trying to find the slope. So we go to the next bit, that is magnification against v. So we have magnification against v. So you are plotting a graph of magnification against image distance. The graph is a straight line graph with a positive gradient. So from the length formula or the mirror formula, if you multiply through by v and then you rearrange, if you multiply through by v and then you rearrange to the form of y is equals mx plus c, then you get m equals v over f minus 1. That's you multiply through by v, that means you get v over f is equals magnification plus 1. Then you make magnification the subject, so you get magnification is equals v over f minus 1. So if you look at this equation now, m is the y-axis, we have v, which is the x-axis. That means slope represents 1 over f. That means if you want focal length, you simply find the reciprocal of the slope. And it's also important to note that the value where this line graph cuts the magnification axis is -1. So that's all about the topics on thin lenses, reflectionate plane mirrors, and curved mirrors, and also linear propagation of light. The linear propagation of light. So I want us not to go to the seventh topic, which is also the last topic for this case. So we have Hooke's law. So for Hooke's law, you are normally interested with determining the spring constant. For Hooke's law, you are determining the spring constant of a spring. Remember, you can also get the energy or the work done. So for the spring constant, we have a spring here whereby you are adding more masses, and then you are getting the pointer reading on the meter rules. Then you plot a graph of stretching force against extension. So the graph is a straight line with a positive gradient passing through the origin. So you realize that if you get the slope of this graph, f over e, or change in f over change in e, f over e from Hooke's law is the spring constant. And that means if you are trying to find the spring constant of this graph, you're simply trying to find the slope. And then it's also important to note that the area under this graph, that is half f times e, half base times height, half f times e, That area represents the work done in stretching that spring, also the energy used or the energy converted. So that's all about the topics that are tested in physics paper 3. And in each concept, in each topic, remember we have said you should understand the concept that is normally tested in those topics. So I want us now to go to the additional concepts. Maybe we have the experiment here, or the practical. We have two stands, and then we have a meter rule which is oscillating, as you can see from the arrows, the black arrows. We have the oscillation of the ruler. Then you can be able to plot a graph of log t against log L. After filling the table of L, time for 10 oscillations, period, log L and log T, then you plot a graph of log T against log L. Remember, we have said that for any graph, you should be able to know how to replace the value of the slope in the equation that you are given. So we may not say much there. Then we go to a meter rule again, and two drains hanging a pendulum bob. Then you are taking time for 10 oscillations. You should also be able to know how to plot the graph, and once you plot the graph, you should also replace the values in the equation, the value of slope in the equation. We have also another experiment here. There's things to do with the quantity of heat. So things to do with quantity of heat, and in this case you're interested with the heat capacity or specific heat capacity, the heat capacity or specific heat capacity, whereby now you are given some hot water, maybe at the 80 degrees Celsius. Then you are measuring temperature after every time. After maybe 5 seconds you read the temperature. After maybe every 10 seconds you read the temperature. So you plot a graph and so on and so on. So you should be able to get the specific heat capacity or the heat capacity from those graphs. So that's all about the second session on the topics tested and the concepts tested. So I want us now to go to the third part on filling of the tables, how you should fill the tables in physics practical, how you should fill the tables. So first of all, number one, fill the tables in units given in the bracket. That means in the bracket they will give you the units where applicable, so you should fill the table in those units that you're given in the brackets. Number two, don't include the units while filling the table, only put the numbers. Remember, already they have given you the units in the table, so you should just fill the numbers. Then we have use the accuracy of the measuring instrument to fill the table. That means, for example, if you are using a meter rule in centimeters, all values should be 1 decimal place. So in other words, what we are saying, when you are filling the table, if you are reading directly from a measuring instrument, then every value you fill in the table should be in accordance with the accuracy of that instrument. Then point number four, use at least 4 significant figures for values obtained using the calculator. Values obtained using the calculator should fill them in 4 significant figures, at least 4 significant figures, but can also be 2 decimals where you have a very big number. For example, if you have 4,523.27 and continuous 275432 and such things, so you should fill at least 2 decimal places for such a big number. But for example, in this table here, we have current, which will be given the values of currents. Then you are required to read the voltage. So that means the practical lies in the voltage row, because that's where now you get your values directly from the practical. Then we have we also have a resistance column row where you are dividing the values V over I, V over I, V over I. But then we have reciprocal of current. Also, you are just getting a reciprocal of currents from the calculators. So it's important to note that if this table has, for example, 7 marks, then most marks will lie in the second row, which is also the real practical, because if you look at the third and fourth rows, you're only using the calculator to get your values. That means for those values where you were getting with the calculator, if all of them are correct, you get 1 mark. But for the other value where you are reading directly from the instrument, then they carry more marks. For example, in this case, each correct value will be 1 mark. That means row 2 for voltage to be having 5 marks, then row 3 1 mark, and row 4 1 mark. And this same case applies to, for example, if you have a table of angle of incidence against angle of refraction, and then you have sin I over sin I and sin R. Remember, you are given the values of the first row, so you are only determining the second row, meaning that is now the real practical. So once you get all the values there, then you get sin I from calculator, sin R from calculator. That means if you have 7 marks, the first row will occupy 5 marks. Third and fourth rows will occupy 1 mark each for correct values, because that's only the work of the calculator. So we go to number 7. When you're filling the table, you should only fill 1 value. So maybe sometimes you may do an experiment 2 times. For example, you're oscillating a pendulum, trial 1, you get a value, trial 2, you get another value. So you should only decide on 1 value to fill. You should not fill 2 values because it will be double work, and which would be try and error. That means you should only fill 1 value for the most appropriate value of the experiment. So that is the third part. We go to the fourth part, how to solve the equations. How to solve the equations in the practical. So 1, understand how you replace the slope and y-intercept in the equation provided. Again, understand how you replace the slope. The slope is very key, and also the intercepts. So you should be able to understand how you replace the slope and also the intercepts in the equation provided. So that means as you do the practical, first it's important to know that the purpose or the reason as to why you draw the graphs is so that you can solve an equation. Remember, we normally say in mathematics, there are 3 ways of solving an equation. One of them is the elimination method, substitution method, and then we have graphical method. And that means that solving the equations is one of the when you are solving the equations, graph or graphical method is one of the methods of solving an equation. And that's why, again, to emphasize, you must understand how you solve the equation by replacing the slope and also the intercepts where necessary in the equation. So for example, you can consider a normal general equation y against x in mathematics. So you realize that if you have the straight line graph which obeys the form y is equals mx plus c, then we have y representing the y-axis, x representing the x-axis, c is the value you read from. If y and x are like that, then it means m is slope and c is the y-intercept, whereby we are saying c is the value you read here. So that means, for example, if you get 5, you can say c equals 5. Then m is the slope, change in y against change in x, you get the value of the slope. So it's very, very important to look at the equations which are obeying this form. Remember, this is a general form, but we are saying y can be anything. For example, y can be voltage, x can be current, among other things. So you should be able to interpret the equations correctly, and sometimes you may also need to rearrange. You may also need to rearrange so that they can occupy this form, y is equals mx plus c, because they must not be arranged correctly. Then number 3, for some equations, you just need to replace the values. For example, you can be given an equation P equals QR, whereby you already have the value of P and you also have the value of R. So you're only looking for Q, you don't find Q. So for this equation here, you don't have to interpret, you just have to replace the values directly. So you just come and replace P 0.85 and R 20.2, then you get Q. But it's important to note that when you are replacing, it's important to work with the SI units. That's why we are saying number 4, work with the SI units. So that's just to remind you again, always work with SI units. So we go now to number 5, the final answer. When you are stating the final answer, which would be maybe in 4 significant figures or more, depending with the value, then we are saying the final answer should have a correct unit. Final answer should have the correct unit. Remember, if the final answer has a wrong unit, definitely the answer also becomes wrong. So you must ensure that your final answer also has the correct unit for it to be valid. And correct units are determined by what you are solving or what you are dividing to solve. So you can do as many practicals as possible to be able to understand more on this or to apply these skills and these concepts. We go now to the plotting of graphs, which is also the last bit, how to plot the graphs in physics practical. How to plot the graphs. 1. The first quantity stated should be on the y-axis, while the second quantity stated should be on the x-axis. So for example, plot a graph of voltage against current. For example, you are trying to plot a graph of voltage against current. That definitely means voltage is in y-axis, current is in x-axis. So that is as simple as that. Then when you are drawing the graph, or when you are plotting the graph, you start with the axis, which should be having quantities and units together with arrows at the end of the line. So when you draw the two axes, y and x axis, in this case, maybe for example, voltage and the current axis, then you must label the quantities and the units. Units are very, very important. So for example, you can say voltage in volts, current in amperes. And that's very, very important. Then we go now to the scale. The scale of your graph. The scale of your graph should be simple, uniform, and accommodating. The scale of your graph should be simple, uniform, and accommodating. So by simple we mean it should have an accuracy which is a small value. For example, one division, the smallest division can be 0.2 volts, for example, 0.1 ampere, 2 ampere, the smallest division on the scale. But for example, if the smallest division on the scale has a value like 0.23562816233 ampere, definitely that is not a simple scale, because it is not easy to read that kind of a scale. So it should have a small value. The accuracy or the smallest division should be having a small value. It should be representing a small value. Then we go to uniformity of the scale. So uniformity means, for example, if you are starting with 0, you can go to 5, 10, 15, 20, 25, 30. That means it is uniform. And not, for example, you say 0 to 5, then next square is 12, next square is 18, next square is 22, next square is 41. So you realize here, in that case, there is no uniformity, because you cannot define clearly what is the value represented by one square. And that means you must keenly ensure that your scale is uniform. It should be uniform. Then lastly, the scale should be accommodating. We have said it should be simple, uniform, and accommodating. Whereby you have seen simple is accuracy should be a small number. Uniform, all value, or every square should represent the same value. Then accommodating. By accommodating, we mean the scale given, the scale you have used should accommodate all the values in the table. That means you must consider the smallest value in your table and also the largest value in your table. So for example, if your largest value in the table is 99, then your scale should be going up to 99 or above 99. But you cannot have a scale whereby maybe the largest value in your graph in your table is 99, and then your graph is heading at 80. So that is non-accommodative. That means for the scale mark, it will be lost. Then we go to plotting. How should you plot? First of all, you should understand that when you are plotting, you should use stars, or you can use a circled dot, a dot which is circled and circled. But mostly I would prefer if you use the stars. Then when you are plotting, you should plot as per the accuracy of your scale. Again, I repeat that. When you are plotting, you should plot as per the accuracy of your scale. By that we mean, for example, if you are the smallest division in your scale, if the smallest division is representing 0.23, for example, if it is representing 0.02 ampere, the smallest division on the scale, if it is representing 0.02 ampere, meaning up to the second decimal, and then you have a number like 0.2326 ampere in the table, then you want to plot it and your scale is only accommodating 2 decimals. That means you should only plot up to the second decimal. So you can plot it being 0.23. You can plot it being 0.23. That means you cannot be able to plot the whole of it. Neither should you drop the second decimal. That means this one cannot be treated like 0.2. If you drop the second decimal in your plotting, definitely you have lost the plotting mark. Then we go to the once you have drawn the line graph, you should not leave it hanging. You should not leave your graph hanging. If it's a straight line, it should be cutting the axis. So the graph should not be hanging, should be at least touching the axis, maybe the x-axis or the y-axis. And then, but if it's for a curve, you cannot extrapolate the curves. That means for curves, you should just leave them as they are. Once you have plotted all the points and drawn your curve, you cannot extrapolate them. Don't extrapolate the curves, but leave them intact as they are. Then we have for the straight line graphs, gradients or slopes should be determined by picking 2 easily readable points. If you want to determine the gradient of a straight line, you should just pick 2 readable points, easily readable points, normally as you do. But now for a curve, if you are drawing a graph of a curve, then for that curve you should only draw a tangent at the point which you have been told. For example, if they tell you to determine the gradient at 0.1, 0.2 ampere, the gradient at 0.1, 0.2 ampere, that means you should go straight 0.1, 0.2, then at that point on where the curve is being touched by that point, then you draw a tangent there. You should draw a tangent you just go to 1.2 ampere in the axis, then you go straight all the way to the point where you are touching the curve, then you draw a tangent there, and then once you have the tangent, you treat it like a normal straight line, and then you find the slope normally, and the units will be normal. Also, the method of getting the slope will be normal. Then we have number 7, the units of the slope. So the units of your slope should be well stated according to what you are dividing or to the conventional units. So for example, if you are determining a graph of voltage against current, slope will be change in volts over change in current, which is volts per ampere. But you may also decide to say, it is ohm, because you know conventionally voltage divided by current gives you resistance. So that means you may also decide to give your answer in terms of amperes. Then we go to the when you are plotting the graphs, we have the method of marking. We have plotting carries 2 marks, scale 1 mark, axis 1 mark, and line 1 mark. That means the total is 5 marks mostly. And we are saying now we can be shortened as ASPL. Axis, the first thing to be marked is the axis, 2 marks, followed by the scale to 1 mark. Plotting, once the axis and scale are okay, plotting can be marked 2 marks, and lastly, once you have plotted your points, joining the points to form a straight line graph which is cutting the axis, or a curve. So that means always axis should start with the axis, and we have seen for axis you just have the 2 lines with arrows, then the quantity and units, quantity and unit. Then for the scale we have seen it should be simple, uniform, and accommodating. Then you have plotting. We have already said you should use stars, but as per the accuracy of your scale. Then line, we've seen it should not be hanging, and you should join the points that are best fitted, the best fitted lines, the points in the plotting. And then if it's a line, don't leave it hanging. If it's a curve, just leave it as it is. So lastly, it's important to know that physics practical normally carries 40 marks, and it takes 2.5 hours. That means should be able to know how much time to take for each practical. Now, mostly it has 3 sections. The 2 sessions, but 1 session has 2 subsessions. So that can be seen to be 2 major sessions, but 1 with 2 subsessions as well. Then the first 10 minutes of your exam should take them to scan through the paper to see the questions you are doing, so that you can be able to plan how you are going to do that work, and also how much time you'll be spending on each practical depending on how many practical you are doing. So you should be able to scan through the paper to organize your work so that you're not caught up with time, and so that you can be able to manage your work well, and also the apparatus you are given to confirm that you have all of them. So that marks the end of this session. You may share your feedback through the comments section, or you can also email us at elearningclassroom1@gmail.com. Remember to subscribe to our channel, the e-learning classroom, and also you can WhatsApp us at 0703 625 764 to book your copy of the handout. Can give you an handout. Just email us and also send us your feedback. Then you can also be able to book an handout, or for more clarification, you may also send your questions. So that marks the end of that session. Wish you all the best. Thank you.